Going to continue directly into the special continuous random variables. Don't worry, I'm going to give you a short recap before we go into the details. Remember our good friend, the random variables, which basically tries to is an abstraction to our experiments that we previously were talking about in detail. Like, for example, when we were rolling a dice, when we were flipping coins, we no longer need to know the exact details, but we assign each outcome to a certain number instead. That way we can have a certain real number to denote the outcome of any experiment. Note here that although here it's each outcome is mapped to one different value, but we don't have to map one-to-one here. More than one outcome can be mapped to the same value, the same real value. And this allows us to focus on what's actually important for our experiment without really having to go into that much detail. So we looked at the concept of random variable, and we also already know that random variables can be described using these functions. So if we're talking about a discrete random variable, then we can use either the PMF or the CDF. Don't forget, this is discrete. And if I were talking about a continuous one, we can then use either the CDF or the PDF. Continuous. Did I spell it right? Yes. So if you are given a PDF of a random variable, you already know for sure that it cannot be discrete. And the same goes if you are given the PMF of a random variable, you also know that it cannot be continuous. These three functions tells us the probability of your random variable having a certain value, but it tells us different things. So here, if this is the value, the probability mass function will give you the probability that your random variable is exactly a certain value, is exactly 2, exactly 3. And a CDF will tell you the probability of your random variable having any value up to xi, sorry. So any value up to 2, which could include 1 or 0 and so forth. And we can also use the PDF to denote the probability, what happened here? To probability between two different limits, in this case, A and B, and we can compute the probability of our random variable having a value between A and B. I don't know what the value is, but it is between A and B. So as you note here, we use these three functions differently. So the first two for discrete and the second two for the continuous random variables. So here we already know that we have two different types. When we were before the midterm, we already looked at the discrete random variables. These discrete random variables, we had 5 that we covered in class. Does anyone care to recall what do we have? I believe the first one starts with a B, second with a B, G, H, and P. Anyone? Now we are going to go on to the continuous random variables. There are also some special ones that we need to focus on because they happen a lot in real life. We can model a lot of events based on these distributions. So this is the menu for today. This is, basically we only have 3. We only have the uniform random variables, the exponential random variables, and the normal random variables. The last one, other distributions arising from the normal, that is a derivation of the third one, of the normal one. We are going to cover them as well, but not in that much detail. We are going to focus a lot more on 1, 2, and especially 3 here. Okay, so before we start, so the word uniform, you probably, I don't know what type of school you went to, but usually in Indonesia, when you went to school, you needed to wear a uniform. Basically, it means that you wear the same thing as everyone else. And that is exactly what our uniform random variable is. It is uniformly distributed, aka the probability of any value is the same. So when we were talking about a PDF about between the probability of your random variable being between a certain limit, A and B, we know that it would be a certain value, right? The probability. But in this case, we actually know the exact value. We know that exactly at every single point between A and B, the probability is uniformly distributed. In this case, we can also write it as X follows the random variable, follows the uniform distribution between the limits of A and B. And thus, this is the PDF, the probability density function of this random variable. So it is 1 divided by beta minus alpha, which is between where it is valid. As you can see here, it is valid between alpha and beta, and 0 otherwise. Out of the limit in which it is defined, it is 0. And since we already know the PDF, if I were to compute the probability between of X being between A and B, well, sorry, this is a typo. This should be a big X, I think. Sorry. So the probability of our random variable X being between the limits of A and B, we can integrate it. And since 1 divided by beta minus alpha, these are our limits, right? It's a number, right? And recall when you integrate, you can take out the constant. And since these are just numbers, these are a constant. So I can just take it out. And thus, if I integrate it, I can obtain B minus A, which are the limits between which we are computing, and beta minus alpha, which are the limits between which the uniform distribution is valid. So be careful. The symbols of B and A are used to denote the limits in which we are computing. So what's the probability our random variable is between A and B? But we also need to know the uniform variable itself, the uniform function itself. Where is it valid? Is it valid from 0 to 6 or whatever? That is your alpha and beta. And as such, we can then compute the CDF as follows. You write it down as like in the bottom here. It should be 0 at any value before the limit, the lower limit of the uniform function. And then between it, it will have the function of X minus alpha and the and the interval itself. And above that, it will obviously be 1. And I have already recapped all of the important properties of a uniform random variable here on this slide that you can use as a reference to look up uniform random variables. So immediately we can go into some exercises. If X is uniformly distributed over the interval of 0 and 10, so we know that it is distributed uniformly between 0 and 10. This is our alpha and our beta, right? Because this is where it is valid. Now I would like to compute. First, I need to compute my CDF. So let me copy this as a cheat sheet so we can follow it up. Copy that here in the corner. There we go. So that is our reference here in the corner. So if we were to compute the CDF, where are you? Here you go. So we would need to compute, let's just do that immediately. It would be obviously 0 for X lower than 0 because our interval starts at alpha 0. And it would be 1 for all X's larger than 10 because that's when we stop having the uniform distribution. And here it would be X, minus alpha, which is 0. And I don't have to write that down. Let's just erase that then. X minus 0 divided by beta minus alpha, which is 10 here, for X less than 10 and larger than 0. So that is first how we can rewrite our previously PDF into a CDF. And now if I were to compute the probability between 1 and 4, remember that we can compute this is the PDF, right? Usually, but we can compute it using the CDF. So I could use fx4 minus f of 1, and thus I can use 4/10 minus 1/10, which is 3/10. If you would want to note this second part visually, you could also do so if you were interested. So if I was gonna denote it visually, so here is my this is my random variable x. Oh, sorry. Oh, x, and this is my fx, or even my fx. And you know here that this is valid from, oops, I should not do that. You know that it is valid from 0 here to 10. So imagine if I know that the area under the curve, our probability is the area under the curve, right? This all should be 0, right? This, should be 1, sorry. So the total probability of everything has to be equal to 1. We already knew that because when we were talking about PDFs, we know that the sum of all probabilities must be equal to 1. So in other words, we know that this should be 1 total over 10 units. And in that case, when I'm talking about between 1 and 4, I could visualize it from 1, 2, 3, 4. This is obviously not an accurate graph, guys, so please forgive me. You could argue that this area, you can just compute it visually as a rectangle, because you know that this is 10 times 1/10, aka 1. So this one is obviously 3/1/10 equals 3 times 1/10 equals 3/10. So you can look at it as a visual. This is a lot easier to visualize, but obviously I don't recommend you to solve it that way, but it can help your understanding using this type of a visual graph. So here, I have the key apparently in the next slide. And as you see here, it's correct. We have computed the CDF as well as the probability between two limits. So I'm going to leave this to you. I do believe that I have the solutions in the slides that I published, so you can look at that on your own time. And probably we should go over the last one because it's the most interesting. Number 3 and number 4, I'll let you do it on your own. But here, don't forget, we have our friend here. Please do not forget this P given F, P, E, F, P, F. And here, if we have the probability of X being larger than 6 and given the probability X is larger than 5, we can also model it using this equation in our corner here. As you can see, here is the joint probability of them, and the bottom one is their conditioning event. And as you note, look at the top, it says, what is the probability of X being over 6 and X being over 5? So that's a little trick here, but if your X is larger than 6, it will always be larger than 5, correct? That is why we can simplify it writing as computing only the probability of X being larger than 6. And thus we can compute the final probability using the uniform distribution. So you have a bus stop. You have buses coming at this stop at 15 minutes interval. So let's assume that this bus stop is not in Indonesia because buses in Indonesia would not come on time. So you can assume that these buses come on time. They come at 7, at 7:15, 7:30, and 7:45. So as you can see from this details, from this sentence, that the arrival of the bus is uniformly distributed between 7 and 7:30. Well, between 7 and 7:45 actually, but in our question, they're only considering between 7 and 7:30. So here, the 7 here is a red herring. You don't really need to think about 7 o'clock here, because if you consider this interval between 7 and 7:30, it's still 7. So you don't have to think about that. What you need to think about is the minutes. So here we have 0, we have 15, and we have 30, 7:30. So I'm going to forget about the 7 for now. So I know, I should not have used red, I'm sorry, but let's just continue. So I know that the arrival of a bus between 0 and 30 is uniform. So I know that it would be something like that, uniform. I know that the uniform distribution, what I know is that it is uniformly distributed between 7 and 7:30, aka minute 0 and minute 30. So this is my alpha and my beta. This is my bottom limit and my top limit of when this uniform distribution is valid. Okay. So now if we look at fx, let me copy that as well as a cheat sheet. Give me a sec. So I've copied the PDF on top. So since I already know my alpha and my beta, I can then immediately compute that this random variable can be defined as using this PDF. So don't forget, before you start anything here, you need to denote your random variable. This is also a step that many of you forgot to do in your midterm. So I'm going to denote X is the arrival of buses at the bus stop between 7 and 7:30. I know that X is a uniform random variable valid between 7 or 0 and 7:30. I know that. And thus I can denote the fx is 1 over 30 minus 0, 30, for 0 x 30 and 0 otherwise. So this is what I know about my random variable. So I haven't solved A and B yet. I've only defined my random variable. This is also visually visible here if I draw it out. So here, this has to be equal to 1, correct? So each of this should be 130, 1 over 30, 1 over 30, 1 over 30, and it is 0 otherwise. Makes sense. Okay, so now I already know that my limits is, oh, I lost my drawing now, sorry. So my limits is from minute 0 to minute 30, and I have defined my PDF as follows. Note that the arrival time, I'll draw that back then. I'm going to change the color though. So between 0 and 30, I have a bus here. I have 7:15 and 7:30. 7:15 and 7:30. So I'm gonna, that was inconsistent of me. We have forgotten the 7. We have left out the 7. So let's just leave it at 15. Okay, so now we are going to look into the problems of A and B. So in this example, in the first one, A, what I am asking is that what is the probability that whoever, the passenger arrives at the stop at a time that is uniformly distributed between 7 and 7:30. I don't know what time, but it is between 7 and 7:30. Find the probability that he waits less than 5 minutes for a bus. So let's look at that first one, less than 5 minutes for a bus. So if the guy, so we know that there is a bus here, there is a bus here, there is a bus here, there is a bus, oops, sorry, this here. But if the guy arrives between 7 and 7:30, I'm going to ignore the 75. And obviously if he arrives between 0 and 30, we can assume that he didn't come in time for the 7 o'clock one. So what is the probability that he waits less than 5 minutes? So let's see here. The waiting for less than 5 minutes, that means he must arrive here at least. So between there, that and there, because he is waiting less than 5 minutes. Or he's arriving here. So there are two possibilities in which he would have waited 5 minutes. Sorry, he would have waited less than 5 minutes. In other words, if I were to write it down, what is the probability that he arrives between the waiting time he arrives between 10 and 15, and the probability that he arrives between 25 and 30. There we go. Sorry, interruption. Okay. So in other words, we can now compute the first one is, forget it's beta minus alpha. Beta minus alpha. Oh, sorry, B minus A, beta minus alpha. So I could write it like that, plus B2 minus alpha 2, beta minus alpha. In other words, 15 minus 10 over 30 plus 30 minus 25 over 30. And here we get 10 over 30 or 1/3. So this is probably the biggest challenge, which is to translate that into the correct mathematical formula. So I think I have the key somewhere here. Yes, I do. So for this passenger to wait less than 5 minutes, he must arrive between 7:10, 7:15, or 7:10 and 7:15, or 7:25 and 7:30. Thus, the probability is as follows. So following the same logic, now that I want to compute what's the probability that this guy has to wait at least 20 minutes. At least, sorry, 12 minutes. So when I say at least, not less than, that means he waits at least that long, right? So he has to arrive between 7 o'clock until 7:03. 7 o'clock, yes, until 7:03 here, or 7:15 until 7:18. And this, I should delete that. And we should, this is the probability that the first one, and this is the second one. And as previously, I can write it down. What's the probability of X being between 0 and 3? And 15 is the probability, and the second one is the probability of X being between 15 and 18. And we can compute the probability as follows. I would like to correct myself right here. I apologize. This is not the arrival of buses. However, the arrival of the passenger, because we are using X to denote the arrival of the passenger between 7 and 7:30. Sorry, my mistake. And then we can then compute the probability as follows. Okay, so I'm going to, so the next distribution, I'm going to ask you to remember something before. When we were reviewing the discrete random variables, we already covered the Poisson distribution. So when we were talking about the Poisson one, we were still talking about discrete, right? So we would get like exact values of every single random variable. That is why using the Poisson distribution, you could compute the number of arrivals within interval, the number of emails coming within an interval, the number of customers coming within an interval. So that would follow the Poisson distribution because I'm counting discrete things. How many people are coming in an hour? How many emails do I receive in a week? And so forth. But if you think about that problem, like, so I I have an interval of an hour, for example, and I want to compute the number of people. That would be Poisson, because I need to know 1, 2, 3 people come, for example, within my interval. But if you think about that, in a certain interval, there are things happening at a certain interval, at a certain rate during that interval. So now, what if I flip that same scenario, but instead of counting how many people are coming in an hour, I want to compute how much time or how much interval passes between one occurrence and the other. So if I do that, then I'm computing time, which is continuous, and thus I need to model it using an exponential distribution. So for example, the exponential random variables can be used to describe the amount of time, well, technically not only time, but the amount of interval until something happens. So how long does it take until the next event happens? So be careful, because in these type of questions, sometimes you would be given the information, like for example, the rate of customers coming into the store follows a Poisson distribution of so and so. But when you are asked to compute something, you are asked how much time passes between the first customer and the second customer. So although the information was given to you straightforwardly as a Poisson distribution, you need to compute it using the exponential distribution instead. So here you can see that it is the same parameter lambda that we used previously, where lambda is the arrival rate per unit interval. So how many customers per hour, how many emails per day, how many offers per month, or so forth. This rate is what we need to use to compute the exponential random variable. We note that we do not need to multiply it with the interval itself now, because previously with Poisson, we would multiply lambda with t, but now we won't, because it's no longer in a certain interval, but we need to know how much time do we have between each occurrence. And thus we can compute it using the exponential value. So if you are perhaps given a problem like it is known that I receive 3 packages per week, 3 packages like from online shopping per week, for example. So I know that I received 3 packages per week. So if the question was to be, how many packages would I receive in a month? If that is the question, then assuming, I'm just gonna round up here, assuming 1 month is 4 weeks, so my T would be 4. And thus my X number of packages per month would follow a Poisson distribution of lambda times T. But if I was asked, okay, then how much time, so I just received the package today, for example, how much time until the next package? Then if I note Y is my other random variable, is the time between packages, then my Y would follow the exponential distribution with the parameter of lambda. So we're talking about the same event, the same information, but there are 2 different things that we are computing. Note that there are 2 different things. Once again, I have already recapped all of the important things that you would perhaps need to compute regarding the exponential random variables in this one slide. So as a visualization, you can note here that the lambda up there is an exponent to E, and each lambda would create a different type of graph. And the graph in this example, as a visualization, you can see that here my lambda is 1, and that is the shape of the distribution like that. And in this case, my f would be lambda e. Oh, apologies, the lambda should be gone from there. Should be just e to the power of negative x and 0 otherwise. And this random variable would be exponential 1. Okay. Exercise time. So we are going to take quite a lot of time with these normal random variables. It's quite long. There's a lot of material to cover. There are various derivations to the normal random variable, various combinations, and this is going to take quite some time. So my target for today is to cover at least the basics, so the normal random variables, but we can perhaps leave some for next week before we move on to the next material. So normal random variables, they are important because most things follow a normal distribution, and also because if all fails, most of the time you can assume that you can model any event based on the normal distribution. Obviously, this is an assumption and it's not always the case. However, it is a very safe bet when you are considering any type of event, because humans are basic, right? So usually a lot of people will fall in the middle. A lot of people will fall in the middle. Some people are a little less. Some people are a little higher. But this is what a normal distribution looks like. It's also called Gaussian distribution and so forth. Not to be confused with the paranormal distribution. So these are other words. So if you go and look up some example questions or maybe other material, the normal random variables questions, a lot of the times are used interchangeably, the term normal with Gaussian, normal, bell curve, Gaussian Laplace, although that's a little less common, but Gaussian, normal, and bell curve, these are used interchangeably. So as you know here, you can describe your normal random variable using their mean and their standard deviation. So as you can see here, we have 4 different normal distributions. All of them are normal. All of them are, the majority of data are in the middle. They have like a bell shape. And then the tails taper off to the left and to the right. So you can see here, we have various distributions. So the red one, the blue one, and the yellow one, all of them are centered at 0 here, but they have different standard deviations. As for this last green one, you can see that it is shifted slightly because the center is not 0, and it shifted to the left just a little bit. So just as what we've learned about this distribution, I believe it was in maybe the first week of courses when we looked at normal distributions, we know that x is a normal or Gaussian random variable with parameters mean and standard deviation. So as you can see here, we can then also denote it mathematically using x follows a normal distribution with parameters mean and standard deviation. So note that if I have different values, so this is my mean, I can have this normal distribution here, then I can probably have another mean here, I have another normal distribution there, and so forth and so on. So it is very useful to know about the normal random variables, as I mentioned, because most things follow the normal distribution. And I have put together a short recap, a recap slide that you can use as reference to compute the normal, the usual things that you may need to compute about normal random variables. Okay, so this is quite useful, you say. But look at all the different variations that could occur. I could have it centered at 10, I could have it centered at 0, I could have it centered anywhere on any real value. I also can have any value of standard deviation. So my shape could be a little higher, could be like narrower, it could be flattened out. There's so many differences here. So as already learned as well in descriptive statistics, instead of trying to compute these details for every single possible distribution, why don't I standardize my normal distribution? I want all of them to be standard at 0, and I want to use the standard deviation, whatever it is, as a unit of measure. And thus, I can have a standard normal distribution by converting my values to a standard value, a standard score, aka z-score that we already covered in descriptive statistics. So this is just the z-score equation, this one here. This is a z-score equation, pardon me. And if we have any normal distribution, the ones with any value of mean and any value of standard deviation, I can convert it into a z-score as follows. And thus I can now say that instead of following the mean and standard deviation of various numbers, it follows a normal distribution with 0 mean and 1 standard deviation of 1. That is also why the standard normal random variable is also often denoted as the zero mean score. And that would simplify a lot of the calculations. So here I already compiled it again, all of the usual things that you may need to compute into one slide. So note here that we have the expectation or mean. Well, it's 0 because everything is centered at 0. The variance is 1, of course, because we did that on purpose. We put the standard deviation as a unit. So all of the standard deviations should be equal to 1. And lastly, our PDF. So this is simplified somewhat from the basic normal distribution because we no longer have the mean and standard deviation of any numbers. Note here that I now have the PDF, which I can integrate to obtain the CDF. The probability up to, remember, if PDF is the probability, is the function that can be integrated to compute the probability between two limits. If I integrate it, then I can obtain my CDF. Be careful. This is also a callback to your midterm. You can integrate the PDF to become CDF, but you differentiate the CDF to make it into a PDF. Don't mix the two up together. So here, if I were to integrate that, just if you believe me, you can integrate it as follows. So if I wanted to define the fx, large F, which is the CDF, then I need to integrate it as follows. Seems simple enough, right? Seems simple enough. I just integrate it between the values in which it is valid, and I can now obtain my CDF. Since we're talking about the standard normal distribution, which is a standard, people made it on purpose in order to make our computations a lot more simpler. This probability, the probability up to the CDF for standard normal distribution, is also replaced with the symbol theta. Is that the theta? Does anyone? So the CDF for a standard normal distribution. So CDF means the probability of my random variable having a value up to a certain number. So the CDF of, for example, of 2, that means what's the probability that my my random variable has a value up to 2. But especially for the standard normal distribution, this is replaced with the simple phi. Don't mess that up again. So phi z basically is the probability, is the CDF of z, aka the probability that z is less and equal to z, less than z. So this symbol here is quite fundamental for many computations using the standard normal distribution. So this symbol, you should remember it. So basically, it is just another symbol that will talk to you about what's the probability of your x being less than z. And note here that if you are assuming a standard normal distribution, which it looks like this, it never changes, it is centered at 0 and it has a standard deviation of 1. When I say, what is the probability of my x being less than z? So if my z is there, then I basically want to compute the area under the curve on the left-hand side. That's what I'm trying to compute. So what is the probability of my x being less than z? That's all of this area to the left of z. And this is the probability, aka the phi of z. So how can I compute this? Area under the curve. Integrate the function, right? So I can just integrate the f, right? Thankfully, since this is a standard normal distribution, which is already made by people to standardize, I could either integrate it manually by myself, but why bother? Since the function is always the same, it's always with the mean of 0 and the standard deviation of 1, it is the same function every single time. I can use a certain table. People have already computed for me what is the probability to the left side of every single possible value. We are going to look at the table in more detail after this. However, so now, obviously, not all questions, not all problems that you will need to solve is as simple as please compute the probability of your random variable being less than a certain value. If it was, then it would be so simple. Then I would just need to look up my table every single time. Or what's the probability of it being less than 0.5? I look up 0.5, I get my answer. But obviously, that's not always the case. So look at some different things. What about the opposite probability? So what I mean by opposite is, if previously we were talking about what's the probability of my random variable being a value up to a certain number, up to z. But what if I wanted to know the opposite? What's the probability that my random variable is larger or equal to z? In other words, that area there, the right-hand tail. I can't look it up on the table, right? Because the table will give me the phi, aka the probability up to, or on the left-hand side, aka the CDF. So if I would needed to compute the larger than, or the right-hand side, I would need to derive it a little bit. So first, we need to look at some properties. So basically, if I recall that the sum of all probabilities, so the sum of the area under the curve must be equal to 1. We established that 4 weeks ago when we first learned about random variables. The sum of all probabilities, this is the cumulative distribution function, it must be equal to 1. We know that already. So if I wanted to compute larger than z, then I can just look up the left-hand side on the table and compute 1 minus. Seems straightforward enough, right? So I could just look up the table for the z and then 1 minus that. Look, the one that I looked up, and I could find my probability. If I look into it a little bit further, then remember that a normal distribution is always symmetric. In other words, the right-hand side will always be the same as the left-hand side. So if I were to take that area on the left-hand side, so instead of z, I use minus z, I can just simply look up the table for minus z. Why do I need to do 1 minus phi z? I could just do phi minus z. So look up, one time look up without needing to do any computations at all. And thus, this gives you how to compute the opposite side of the probability. Because once again, your table will always give you the left-hand side. Always, always, always. That standard normal table gives you the area on the left-hand side, alias the probability up to. But the probability over is not given to you, so you need to figure it out on your own. Okay, so additionally, based on that concept, you also need to know, I'm going to introduce to you the ZA notation. So it's not exactly the same. So where's my pen? Oh, here it is. So the Z alpha notation basically means that if you are looking to the probability that a standard normal random variable is greater than that particular value is ZA. So if I were to say that, say I have this standard normal variable, and I know that this probability here is equal to 0.05. Just for example, I know that 0.05 of the population will fall in this area here. Whatever value I need on my x-axis to draw that particular line, that is the Z 0.05. So whatever it is, maybe the Z is 2. Sorry, that's not possible. Maybe the Z is 2, or maybe the Z is 6. I don't know. But whatever value this is, this point here on the x-axis, that is Z005 or Z alpha. In other words, so for example, this is my standard normal deviation. I want to find the point at which 0.1 of my population falls here. I want to find the alpha is 0.1. In other words, 0.1 parts of my population will definitely fall on the right-hand side of this. Whatever value it is on this x-axis that I used to draw that line, that is Z0.1, and that is valid for any value of alpha. So here we've put together a basic step-by-step how to finish or how to solve any probability of a standard probability computation of a standard normal random variable. So usually you start with a known distribution. This may not be standard at first. You have a certain mean and you have a certain standard deviation. As I mentioned, that means that your bell can be centered at any point, and it can also be either narrow or very, very wide. We don't know yet. But we don't want to compute that. I want to compute the standard normal one, the one that is centered at 0, the one that has a standard deviation of 1, so that I can just look up my table. I don't need to do any computations. So the first step is to convert your normal RV into a standard normal one. So note here that here my X, the one that I'm computing, is still a basic normal one, right? And I would like to compute it, I would like to convert it into a standard normal one with the 0 and 1 as the mean and the standard deviation. So what I do is I can just compute by minusing with my mean and dividing with my, careful, variance, not my standard deviation. So here I need to take my variance and not my standard deviation. So here you can note that X minus mu divided by this is my Z, obviously. And here I will end up with a certain value, a certain number here. And thus I can immediately compute the probability by computing. There's one part that's a little bit skipped, which is the CDF, F of B minus that minus F A minus mu divided by variance, aka phi and phi. So now we are going to go into some examples, but before that, we are going to look up a standard normal table. So in order to do that,
I'm sorry, ma'am, I think you're muting.
Thank you. And I just started recording. How embarrassing. Thank you very much. So these are some ways to compute the probabilities of a standard normal random variable from a normal random variable that may not be standard. What you need to do is first convert it into z. And if your random variable x is minus mu divided by standard deviation, it would turn into z. And then you can follow on with that, with the computation, and use the table to look up your value. So here, I think I still have some extra exercises. You can try that out on your own terms. Oh, just don't forget that in this case, I'm not going to finish this until the end. Just recall that in this case, when I'm doing that, I need to do 2 minus 3 divided by 4x 3 4 and 7 3 4, which will bring me to the probability of negative 1/4 z 1, I think. Yes. And since we're computing between, we can then convert this into the probability of z being less than 1 plus, minus the probability of z being less than negative that, and then we can get that using the thetas. There you go. And you can check the final answer on your own. Pause here. Any questions? So now that we have established both the normal random variables and the standard normal variables, you probably have already gotten a feeling that, oh, wow, this is quite an important distribution. That is correct. A lot of things in the world will follow the normal distributions, and many derivations are built on top of the normal distribution. So in the next class, we are going to look at what happens when we combine some normal random variables. If I know that there are 2 random variables that are both normal, what happens if I combine them? You can see that we have different examples here. We have a linear function, we have sum of blah, 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 we have linear combinations and so forth, which I'm not going to go into detail now, but we'll cover it in our next class. And lastly, we also have some derivations from, I'm going to skip there. I'm going to go over some derivations of distributions arising from normal distributions. The reason why we have these distributions arising from the normal distribution is because the normal distribution is an ideal setting, right? Oh, it's a bell, and it's centered at 0 if it's standard. I can simply define it by defining the mean and the standard deviation. They are symmetric. All of these are ideal cases. However, obviously in the world, it's not always that ideal. So this shape here that we have, this bell, we can like tweak it a bit. Perhaps we'll stretch it out a bit. Perhaps we'll skew it a bit. And then we can have a distribution that perhaps can fit our phenomenon a little better. So I'm intending